Okay, I want to take a look at some arithmetic of vectors. And so in this video, we're going to focus on something called scalar multiplication involving two-dimensional vectors. Scalar multiplication with two-dimensional vectors. All right? Scalar multiplication with two-dimensional vectors. So first of all, what is a scalar? Well, in two dimensions, a vector has two components. It has a horizontal component and a vertical component, right? It requires two numbers, all right? Two numbers it takes to create a two-dimensional vector. So a scalar is simply one number, some constant c, some number c. So this is a vector, this is a scalar. So how do you multiply a scalar by a vector, and what does it mean? That's what we're going to look at here. So let's say we want to consider, how about 2 times the vector. Let's say we've got the vector -4, +5. So let's consider that vector. What this means is if you take the vector -4, 5, which looks like this, so left 4, up 5, maybe I went a little far there, left 4 and up 5. So the vector -4, 5 looks like this. Then the vector 2 times -4, 5 just multiplies all of this by 2. And so this is the vector, let's use purple. This is the vector -4, 5. And so if you look at the vector 2 times -4, 5, oftentimes you don't draw these, by the way. I'm just explaining what's happening here. 2 times -4, 5, the -4 turns into -8, twice as long, and the 5 turns into 10, twice as long. And so the vector 2 times -4, 5 is now this vector. They are exactly proportional to each other. The triangles all have the same 3 angles, so they're similar triangles. So all the angles match, right? So we could indicate that like this, maybe, showing congruent angles. And of course, this is a right angle in both cases. And so another thing that's true is that whatever the length of the purple vector is, you would multiply that by 2 to get the length of this new vector, 2 times -4, 5. But more importantly, how do we describe this new vector? We don't describe it as 2 times -4, 5 usually, because since it's a vector, we can describe it using components, just components with no scalar being multiplied by it. And you can see from the picture, this vector has a horizontal component of -8 and a vertical component of 10. So can you guess, if we didn't draw any pictures, how would you multiply the scalar by the vector? Well, it's very easy. You multiply each of the components by the scalar. It looks like the distributive property in algebra, okay? 2 times -4, 5. Well, 2 times -4, 5 is this new vector -8, 10. Very simple, right? And you also can see geometrically what happens. The scalar just scales, if you will, scales your vector by that factor. So if this was 1/2 times the vector, it would shrink it by 1/2. If it were a negative number times the vector, it would reverse all your components, and so it would point in the opposite direction and then scale it to a different length, okay? All right, so I mentioned that it looks like the distributive property. In fact, let's take a look at a different notation for vectors that shows why we like this particular notation. So this -4, 5 can also be written in terms of the unit vectors I and j. So I could write this as negative 4 times the unit vector I hat plus 5 times the unit vector j hat. And so now I've got that vector times 2. This way of writing vectors helps you connect it more to algebra because they share a lot of algebraic properties that you're used to, like the distributive property. If you think of I and j as being variables, then you can think of distributing the 2 to get negative 8 I hat plus 10 j hat. And that's precisely the same vector as the vector written in angle brackets, negative 8 comma 10. So either way, you get the same answer. This lends itself maybe more to intuition than what we do up here. But in either case, scalar multiplication is really that easy.